Okay, so this would be our first problem trying to solve for displacements using virtual work in a beam. So if you look at the problem, I've got values of E and I, so I can get numerical results. So I got a simple supported beam with a single load of 16 kips at B, and I'm looking for the displacement at C. Okay? So remember, in virtual work, the first thing we want to find is the virtual or the real moments and then the virtual moment. So let's start with that. Let's see if I can write an equation for moment across this structure. And just to remind you, I'll put that I'll do everything from left to right for my x-coordinate. Now the first question I need to ask you is, can we write a single moment expression for the variation of moment across this structure? No. Right? Yeah, so we've got high probability that answer is no. So we're going to have to write one expression that's good from A to B, or the first 10 feet, and then a second expression that's good from B to D, from 10 to 40 feet. In both cases, I'm going to need my reactions. So I'm going to start by assuming that I have a reaction at A, up, and a reaction at B that's also up. Now I didn't assume shear because I'm not really interested in writing a shear equation, I just want moment. So I'll try a little different approach this time. So at this point, to find those reactions, I'm going to sum moments about one of the pins and then sum forces. I'm just going to start off alphabetically, and I'm going to sum moments about A over here on the left side and set it equal to 0 for equilibrium, and I'm going to assume right-hand rule. So I'm looking at how the moment about A for my various forces, the applied force is going to create what kind of moment about A? Positive or negative? Negative. So there's my negative moment. The force is 16 kips, and the distance from A to B looks like 10 feet. The next force in the system would be the reaction at B, and that's going to create what kind of moment about A? It looks like it's going to be positive. The force would be RB, reaction at B, which I don't know. And the distance between A and B looks like 40 feet. So it looks like my reaction at B is going to be 4 kips. Does that look right? And then if I sum forces in the vertical direction, in this case I'll call that Y, and make sure I'm in equilibrium, I'll assume up is positive. So my reaction A is up, my reaction B is up, my applied force 16 is down. So I have reaction at A plus the reaction at B minus 16 kips. Well, I know my reaction at B is 4, so my reaction at A would be 12 kips. With those values, I now want to find what I'll call my real moments. So as we discussed before, I want to find it between 0 and 10. So I'll put a little label there that this moment is going to be for the first 5 feet, and I'll draw a little free body diagram of that at some distance x. And right now all I'm interested in is the moment, so I'll assume positive moment. And of course I've got my reaction at A, which was up and equal to 12 kips. So that's not too hard. I should be able to find that moment pretty easy. All I have to do is sum moments. Again, I'll assume right-hand rule, and I'll sum the moments at the cut I just made and make sure that's in equilibrium. So the internal moment with my sign convention is positive, and the moment about the cut, due to the applied force, which is the reaction at A, that creates negative moment. The force is 12 kips. The distance is x. So it looks like my real moment in the first section is just 12x.
Why did you do 5 instead of 10?
Say that again?
Why did you do 5 for the distance that you cut it?
I'm cutting it at an arbitrary distance, right? I'm cutting it anywhere I want here. I'm looking this way. So I can be anywhere between, oh, you're right. Why did I do that? This is not 5. This is 10. Sorry, thank you. The equation is unchanged, but the limit is, I don't know why I did 5. Sorry about that. So let's see if I can get the next one right. So the next one would be from 10 to 40. In that case, I'm going to cut and look at the right section. So the distance up to the cut would be x. So this is, I'm always measuring to the right, so that was x. So the remaining segment that I have here would be 40 minus x. At the cut, I still have positive moment. And on the right-hand side, my reaction at B was 4 kips. So I'm cutting it somewhere here and looking to the right side. So again, I'll use right-hand rule for my sign convention. I'll sum moments at the cut. Make sure it's equal to 0. And what do I have? Well, internally, this moment with my sign convention is negative. And then about the cut surface, the reaction creates positive moment. That's 4. And the distance is 40 minus x. So it looks like my moment will be, and I'll expand that, so that's 160 minus 4x. So I'll rewrite that as minus 4x plus 160. Now I can check these, right? I know that the moment at x equal to 0 is what? It's a pin, so it should be 0. And you put in x equals 0, what does this moment give you? It gives you 0, right? So that's okay. I also know over here that the moment at x equal to 40, which is D, well, that's an external roller. That's also 0. And if you put in x equal 40 here, what do you get? You get 0. So that's nice. And at the point they share, which would be x equal 10, so at x equal 10, according to this equation, you plug in x equal 10, you get 120 kip feet. You come over here and you plug in x equal to 10, what do you get? You get 120 kip feet. So they match there too. So that makes me feel pretty good that I got my real moments right. And this would have been enough for exam 1, right? Now we're maybe halfway through. So we have to do it again. So now we have to do our virtual system. And I'll try to use the lowercase m for that. Now the first thing I have to do is I got to rework this whole problem. So I'm going to go back and draw my structure. Geometry does not change. Unlike conjugate beam, I don't have to change the space. But I do have to change this. It says I want the displacement at C. C is right in the middle. So my virtual load now is right in the middle of unit 1, or value 1, no dimension, and that will be at 20 feet and 20 feet. So now it's like you're working a whole new problem. In fact, I'll kind of put a little squiggly line here, kind of separate that from this. Now, can I write one virtual moment expression for the whole structure? No. What have I got to do? Well, I've got to write one that's in here, and I'll probably go to the left side. I've got to write one that's here, and I'll probably go to the right side. So I'm going to repeat this process, but now with the virtual load.
And you put the load on the middle?
I put the load here because I want the displacement at C, and C is in the middle. Remember, you apply the virtual load at the point you want the displacement, and I'm assuming it's going to displace down, which seems reasonable. So I'm going to have, in this case, a reaction at A. In this case, a reaction at B. If I can squeeze this down in here. So I'm going to sum moments at A. Make sure it's in equilibrium. So my virtual load about A creates negative moment, unit of 1. The distance from A to C is 20 feet. And then the moment created by the reaction at B about A is positive. And the distance is 40. So it looks like my reaction at B is 1/2. That makes sense too, because I have a unit of 1, a load of 1. It's right in the middle. You'd expect that half the load goes to one side and half goes to the other side, and it does. And just to finish that, if I did sum forces vertically in the y direction, make sure that's in equilibrium. Both my reactions are up, so they'll be positive. So the reaction at A plus the reaction at B. My unit load is down, so that's -1. So it looks like the reaction, I did that wrong. This is the reaction at B. This is the reaction at A. It's 1/2 also. So both my reactions are 1/2. Okay? So now I find my moments. So I'm going to start with the first one, which is between 0 and 20. So my free body diagram for that looks something like this. The reaction on the right-hand side is up and equal to 1/2. And then here's my internal virtual moment, positive. And then, of course, the distance to the cut is x. So when I sum moments about the cut surface and make sure it's in equilibrium, I can find this internal moment. And you see that's not too hard. I'm using right-hand rule, so this internal moment would be positive. The moment about the cut due to the 1/2 force would be negative. So force times distance. So the virtual moment will be just x over 2. And let's do it again on the second half of the beam, which would be from 20 to 40 feet. And that free body diagram would look something like this. So the reaction on the right-hand side is the reaction at B, which is 1/2. This is my positive internal moment. And then, of course, we're measuring from the right. That's x. So the segment length that's left over on the right-hand side would be the length of the beam, which is 40 minus x. And just solve for that internal moment there. So again, we'll sum moments at the cut. Make sure everything's in equilibrium. Since I'm using right-hand rule, this internal moment is negative. And about the cut, my reaction moment is positive. And that'll be 1/2 is the force, and the distance is 40 minus x. So my internal moment, doing my arithmetic, looks like minus x over 2 plus 20. So if there is hard work, it has been done. So all we have to do now is write the virtual work expression. And I didn't. Does anybody have a blank piece of white paper they can lend me? Does anybody have a piece of paper like this? Nobody? Well, maybe I can flip it over on the back. That might be a little tricky to do. I'll tell you what I'll do is I'll cheat and use the back of this paper. So let's see what our expression will be now. So the displacement at C is normally going to be written as the integral from 0 to 40 of the real moment times the virtual moment divided by EI dx. Now when you look at this limit from 0 to 40, we have to count for all that space. We know the real moment, which I'll slide down here and show you. The real moment is one of the equations is valid from 0 to 10, and the second one is from 10 to 40. So I'm going to probably have to go from 0 to 10 for one of my increments. But notice that the virtual moments are what? 0 to 20 and then 20 to 40. So I'm going to have to go from 0 to 10, this real moment, this virtual moment. And then I'm going to have to go from 10 to 20, switching to this real moment, still matched with this virtual moment for the 20. And then finally switch to this real moment and the second one. So that's 3 segments. So I'm just going to write it this way first. So I'm going to have one from 0 to 10, plus another one from 10 to 20, plus a third from 20 to 40. And that subdivision of the space is guided by the limits of the real and the virtual expressions. So with that as the background, let's see if we can get it. They all have EI as a constant, so I'm going to factor that out, just so I don't have to carry it around. So what I'm left with is the first integral from 0 to 10. So that's my real moment, 12x, and the virtual moment in that space is x over 2. Okay? Now the integral from 10 to 20, well, I have to switch over to the real moment that's valid from 10 to 40, which would be minus 4x plus 160. But I still have to use this virtual moment because it's good till 20, which is x over 2. And then finally, the last bit, from 20 to 40, I'm still using this real moment expression, but I have to switch over to the other virtual expression. Now you can see we've been working at this for quite a bit, like almost 20 minutes. And now what we've come to is this, which I'll call the virtual work expression. That would be enough for me on the exam. Because even given enough time, the comfort of my office, some appropriate music, good hot cup of coffee, it would still take me another 4 or 5, 10 minutes to do all that, check it, and run the numbers. And that's really not my objective. My objective is for you to get to this point. So this would be good enough for the exam. Is this good enough for mastering engineering? No. You have to go all the way. So what I'm going to do is I'll stop the video here, but I'll go ahead and go back to my office in the comfort of my environment with music and a hot cup of coffee, and I will finish this and let you see the numerical value. Okay? So any general questions about that before we move on to another problem? So let's just review. So the idea is you write the expressions for moment for the real loads, whatever those might be, and you might get several of them depending on how the load's applied. And then you apply the virtual load, which we're assuming is a unit of 1, at the point you want the displacement in the direction you think it's going to occur. And then you look at that problem. It's almost like I have a new problem now. This is my problem. And then you find what are the appropriate moment equations for that scenario. And then the third concept or skill would then be matching them together over the right intervals to construct the virtual work equation. Now again, looking at that, these are pretty simple integrations to do. They're all polynomials. But evaluating these limits, again, not hard, but super tedious. Lots of time, lots of places to make mistakes. So this is going to be good enough for me for our exam. Any other questions or comments before I stop? All right.